Okay, so a few weeks ago I did a tutorial where I showed you how to set up PyTorch, and I did like a very simple example to demonstrate that I was working on our GPUs. That example was there's a public data set of clothing images, and it used it to A, train a model to recognize clothing images, and B, pick out, look at some clothing images and pick out what it thought they were. I thought there's another framework, which is not PyTorch, called Tensorflow, which is quite popular. Tensorflow is fabulously annoying to install, and you're pleased to know that I have a previous draft of this video where I got half the way through this process and then just gave up and lost my temper. So let's try this again. TensorFlow is by Google. That means everything is based on Google's not invented here problem. So it depends on lots of libraries that Google wrote that do things that other libraries other people wrote also do, but you do not have installed on your system. For a while now, TensorFlow has been packaged as wheels in pip, like PyTorch. Those wheels variously work. At the moment, they kind of work, so we'll use those. Sometimes they don't work because your version of Linux is too old, in quotes. There was a significant period of time where the Google engineers were not able to build their version of Python 3 with OpenSSL on, I think, Ubuntu 18.08 or 18.04 or 16.04, wherever they use as a proxy for Red Hat, which meant that their wheels didn't work on Red Hat. That appears to now be fixed. But there's still a whole bunch of layers that you have to worry about when you're making this work. Let me go to, so I'm at the TensorFlow website here, obviously. We go to install. This gets quite complicated, right? There's a whole bunch of stuff here. You can compile it from source. That is, well, if you look at my head, I'm quite balding. A lot of that is to do with having compiled TensorFlow from source a number of times. It has a build system called Bazel, which is horrendous. Bazel is horrendous because it's another Google product, of course, that's really intended to build completely clean builds of the Android operating system, no matter how screwed up your machine is. And the problem is, with most HPC codes, what you're trying, and this includes things like TensorFlow, you're trying to build for your machine and this specific environment, and Bazel removes all of that information, and it makes things that just don't work. But luckily the wheels work. So we also want to run on GPUs. I have got a session in one of our nodes with a V100 in it, so we should be able to do a GPU test. I have done a dry run through this, so mostly this works, although it's slightly annoying, and so let's go through it. So, TensorFlow. We should look at the instructions for pip. They've got instructions for Docker here, which you could use if you had a system that allows you to do that. You'll notice that even when installing with pip, they want us to use Conda. Conda is also horrendous, and we're not going to use Conda, and that's why we're going to make our lives difficult for ourselves. So what we're going to do is we're going to set up virtualenv in Python 3.9.10. We are going to install TensorFlow on it. We're going to prove that it works on CPU. Then we're going to install CUDA and CUDNN on there as well. And then using the session we have on the GPU, we'll prove that it also works on the GPU. Right. Let's bring my shell up. So, I am logged into Myriad here. I've created a folder called TensorFlow demo. As I said in the previous video, my environment is slightly different from everyone else's. I don't have the Intel compilers in my environment by default. And that's just because I do so much stuff that doesn't involve them that it's better I just don't have them loaded. So to get to the state, you do module remove compilers MPI, and then you'll end up in the same state as I'm in currently. Again, I show that in the PyTorch demo. So the first thing to do is we need to add Python to our environment. And then we want to create a virtual environment here. So I will just call it TF. Let that sort itself out. We've created the virtual environment, then we do pip install. First thing I usually do is upgrade pip, because on these machines it can get out of date, so I think this one should be up to date. Yep. Oh, I have missed a step. we go. Of course, I need to activate the virtual env. Okay, that'll do pip. Yeah. Okay, so the next step is to install TensorFlow. If we look at installation instructions, it says that with pip we do just pip install TensorFlow. You can see that I did it right wrong because there's a copy of it in my cache. One of the real challenges when you're compiling this from source is that Bazel downloads the source for all of these dependencies and compiles them. And some of these are programs written in C++. And because Bazel strips a lot of the environment information from your environment when it's building things, you then build versions of these that don't work, right? I mean, again, just Bazel is terrible. I will link a talk. There's a talk by a guy called Kenneth Host, who is the developer for EasyBuild, which is one of these packaging systems for scientific applications. He talks about some of these issues, and it's a really good talk, so I'll link it below. Right, that's installed. So now if we run Python 3, and we do import TensorFlow as TF, it should load it, and it should spew out a lot of worrying warnings. So first thing it does is it says it's compiled to use some instructions we have on the Skylake processors in Myriad, AVX2, AVX512F, and FMA. That's good. When it's making use of this library 1 DNN, it's not using it for the rest of the code because the TensorFlow wheel is designed to run on lots of different machines, and your processor might not support those. So that's why it says here, it says we can build it from source if you want to enable them, but actually these are in the routines that do the matrix math, which is where they fly anyway, so it doesn't really matter. It then complains that it can't find the CUDA drivers. That's because we haven't installed CUDA. We're on a login node, there's no GPU, so we can't really test that at the moment. Then it has a separate set of errors about the lack of TensorRT, so we are definitely not going to do TensorRT today, because I had a look at that when I was going through the dry run, and it has a set of requirements which contradict the set of requirements for CUDNN. So we're just not going to do that, but that's used for inference and speeding up inference, so we're not going to install TensorRT. But other than that, it's working, right? So we can run it on CPU. So if we quit out, and then tail up using MATLAB. If we put a program in there, so what will we do? So we're going to do that fashion example, right? And that's available, coded up. Here we go. So there's a walkthrough here on the TensorFlow website. In the tutorials, basic classification images clothing. This is the same steps. You'll recognize these grayscale images from the PyTorch video. The training set and the test set are the same. Our beloved ankle boot will reappear. And the code for this is in GitHub, and I pulled out the bits which do commands. And if we copy that from the test folder, we get, oops. It has, the same steps as we had before with the previous version, right? So we pull in some libraries, including that term show thing. So I have to remember to copy that in as well. Print the version of TensorFlow in the same way that the data set you can pull in automatically, because it's a public data set that's used for a lot of actually demos like this. It's already in TensorFlow, so we can just tell it that that's the data set we want. We pull out the training images and labels and the test images and labels from that data set. We make sure we've got the class name set up, good old ankle boot. So the images are stored as grayscale images, where the grayscale is a brightness from 0 to 255. We need to rescale that into floats, so it's 0 to 1, just like they're represented in PyTorch. Set up the layers of the model, compile it, and then do training using the training images to train the model over 10 epochs. Then we can test the loss function, which gives us a rough estimate of the accuracy, evaluating the test images. And then we had a final layer, which gives us So when you run the model, it will give us probabilities of a particular answer rather than just the raw information. So we add a probability layer. Then I'm going to use my little horrible term show library to show the first image in the test set. We're going to do the predictions, and then we're going to print the name in the first of the predicted type or class of the thing in the first test set, and hopefully that will be ankle boot. Right? Let's copy term show, or rather link it. Right, so we have fashion, we have term show. We should be able to run this on the login node here. It should execute correctly, but it'll be running on CPU. So let's do this. We go in our training, right? There we go, there's our picture of the ankle boot, and it has indeed decided that that's an ankle boot, so that's good. So TensorFlow is working, but it's only running on CPU. Now we get into the painful part. So, starting on GPU, we need to give it, I can close that now, we need to give it CUDA and CUDNN, right? And the installations have links to these things. It definitely, so the other thing is TensorFlow is incredibly sensitive to the versions. And we have both these SDKs installed on Myriad, but we have newer versions than TensorFlow is built with. And again, I tried this yesterday and they don't work. So we need to get a new copy of the CUDA toolkit 11.2. That's relatively easy to get. NVIDIA make this available as an archive releases page. You go and get 11.2. And then there's this, this menu will be familiar if you install PyTorch. This is a similar thing with Linux, x86-64, Red Hat Enterprise Linux 7, and we want the run file version. And if we hover over that, it will, I don't know why it's got, oh, because it's got a Twitter embed, I see. If you click on that, it will give us a file to download. So let's get that. I'm going to create a directory here. And that will download. It's 2.8 gigabytes, that's quite a lot of stuff, but Myriad has a fast connection to the net, so it's not as bad. CUDNN is a different proposition. So, while that's going, if you follow the instructions here, you'll go to the CUDNN SDK website, click download, and it will then ask you to log in because this is top secret NVIDIA stuff. It's not really top secret NVIDIA stuff because they have lots of packaging solutions that download it automatically for you without you logging in. I logged in because I have an account because I've done it before. I downloaded the right version as described here, and that seemed okay. However, I am quite a paranoid individual, and if you look at the instructions, they say, for example, for the Cruelty Toolkit, download this and then just run it. That's not a great idea. It's not a great idea to grab a binary off the internet and just run it. You should have some verification that it's not malware. I mean, this is from the NVIDIA website, so it's probably okay. But still, what I like to do is there are a couple of projects that do automatic package distribution, and they are a tool called SPAC, which I didn't actually bring up as a link because I use it installed. Which is a package manager that focuses on scientific applications. I believe my user support team are about to move to using this to deploy on our services at some point later next year. And similarly, there's a version of Linux called Arch Linux, which I don't use ever. I don't have it installed on anything except hilariously my Steam Deck where it came pre-installed. But one of the things it does, it has a very active community managing a thing called AUR, which is community managed packages. And so I use it a lot because they have like a valid third-party hash for a lot of packages. Specifically, looking at CUDNN 8.1.0, if you look at the Git for the thing, you can see that the SHA-512 checksum for it is this. Similarly, I have SPAC checked out of GitHub in here. And if we go into the CUDNN directory, you'll see there's a thing called package.py. And inside package.py, there's a list of versions and hashes. So when it downloads this package, it checksums it to make sure it's got the download has not been corrupted and there's no one in the middle trying to do anything malicious. Here is a problem. So if you go through the process of logging into the CUDNN website and download the file, you end up with the following. You end up with this file here, which I've called CUDNN 11.2 Linux x86b81077tg updated. This has a different checksum from what is in both of those packages in systems. So AUR has a checksum in SHA-512. SPAC has a checksum in SHA-256. They do not match the file you get, which is pretty sus. I ended up looking at the URL you get, and let me just see if I can pull out. Of course not. That ends up it being in a directory, if you look at it, which has like a date on it as well as a version number of CUDA. So what I think has happened is that NVIDIA has quietly updated the the CUDNN package sometime in January 2021. And they've done, in a way, they've done the right thing, right? They've not replaced the original package. They've put a new copy and given it a new URL. Because if you look at the way SPAC and AUR work, they pull down a version from a different URL, and that version definitely matches the checksum, right? So I think maybe I have to do it here actually. History, rep, NVIDIA. No, sadly that is still the CUDA one. Okay, fine. Anyway, long story short, I have two copies of this, one of which both downloaded from NVIDIA, but one of which matches the checksum and one of which doesn't. I'm a very paranoid person, so I'm not going to install the one which doesn't match the checksum. I'm going to install the one that matches the checksums that are in AUR and SPAC. You are free to be not paranoid. Regardless, this had me stumped for a bit. It is possible to work out from SPAC and AUR what the correct URL is for the original version of this package. Right, so we end up with, so I've created a file here called checksum.txt. That has the checksums from SPAC. I downloaded from the URL in AUR, so I have two sources of truth. They match. And so I will copy the checksum file into the directory below. Oops. And I will copy this tar.gz, which is the one which matches, rather than downloading it. Okay, so when you've got your file with the checksums in it, you can do this. You can see it, they match. Right, so having done that, we now need to construct a situation where CUDA and CUDNN are installed. There are more stumbling blocks. CUDA likes to unpack itself into /tmp in the on the hard drive on the compute node you're on. This is not going to work because /tmp is very small. So we have to change this variable you might know from your scripts, and we'll make it in my scratch directory. Okay, we need to make the CUDA installer executable. Okay, and then we need to run it. The first thing I'll do is wait for a few minutes while it unpacks all its temporary files into Scratch. And then it will give us a very fun interactive installer. And part of the reason this works, right, is on the NVIDIA, on the compute nodes with the NVIDIA GPU, they have the drivers already installed, and those drivers actually match the version in here, right? They are 11.2 version of CUDA, and they are 460 version of the driver. So it asks if we're now in this interactive program, right? This is somewhat automatable, but let's just go through this. We accept the end user license agreement. So we need to change some of these options because we're not root, right? So we can't install the driver. I don't care about the samples, the demo suite, or the documentation. We do want to change the options for the toolkit though. So we want to change it so it installs to home, UCCIRT, that's my user ID, Scratch. What did we call this? Tensorflow demo. And then TF, because that's what we called the virtual env. We do not want to create a symbolic link. We do not want to create desktop menu shortcuts. We do not want to install man page documents. Okay, now do install. Right, there we go. Fine, so that's now installed. If we actually look in that directory, that's actually where we installed the Python environment. So it would be nice if Python virtual envs were good enough that we could just activate the virtual env and have it work, but again, as part of the process I discovered that's not really the case. But it should work with path at least. So we should actually, if we do like which nvcc, we should get the one that was just installed because it's in the virtual env we have loaded, and therefore the environment variable path is set. What is not set is load library path. So load library path is the path that LD, which is the Linux runtime linker, uses to find dynamically linked executables. So we need to set that. And then what we want to do is put that in. So let's do /home ucc /scratch /tensorflow demo tf lib64. And then because we're prepending it, we want to have the original LD library path as well. It's a very bad mistake if you don't do that, because lots of things will suddenly stop working and you'll be stuck, including things like ls, I think, on some systems. So if you do sorry for the background noise, by the way. This is it's getting towards the evening, and the education team are in here, and they're quite loud towards the end of the evening. Right, so that now includes that path as well as the other stuff that makes other libraries on my system work. We'll have to do that in every shell. That's quite annoying. So what I'm going to do is I'm going to start a script that we can source with those settings. Right. So if we call it setting. Okay. Right. Now we need to install CUDNN. CUDNN is also annoying because That's what everything in machine learning is like. If you go to the NVIDIA folder, so you unpack it with tar. It assumes you're unpacking it in a directory called CUDA. Don't know why. That's not a great assumption. Anyway, what this means is we now need to copy those files into the equivalent directories inside inside our virtual env. So once that finishes unpacking, if we go down to that virtual env, and we do cp-r /NVIDIA CUDA star. Okay. And then we need to do the same with the include files. Okay, so that is now cudn installed manually. There is one other thing we need to set, and that's quite an annoying setting. In order for Tensorflow to find this, despite the fact it's in the library path, CUDA is in the path, you would think that'd be enough. There's another variable we need to set called XLA flags, so let's put that in the settings as well. Oops, what did I call it? Environment. Shit. Right. As well as that, we need to do export XLA flags equals and then the same. It's effectively the same. So we need to tell it that this is where CUDA is installed. Right. So we now have our environment file, we have our script, we have a virtual env which has CUDA installed in it and TensorFlow installed in it and CUDA installed in it. I have a shell on GPU node. Now, when you're actually doing this in production, you could ask for a job interactively like this, but you're going to wait and it's going to be annoying. You should obviously create a job script, and I'll create a job script to show you what that should look like at the end of this. We won't get to see it running, but I'll show you what it should look like. Right, so here we are. So we're on a node. It is a Tesla V100 PCI Express. Fine. It's got CUDA 11. The driver installed is driver 460, which corresponds to CUDA 11.2, which is the version we're using in TensorFlow, which is good. So coincidentally, things match. We like that. That makes life easier in GPU land. We're in my home directory. So first thing we need to do is add Python to the environment. You need to go into the TensorFlow demo directory. We need to activate the virtual env. We also need to source the environment.sh. Right, and that should mean that XLA flags is set correctly. Let's check that just to make ourselves extra super happy. Oops, that's not how you do that. Okay, that's good. Now, in theory, everything is in position. We should be able to run our script and it will run on our GPU. Let's see if that happens. So, it's still complaining about the compilation stuff through the processor. That's fine, we don't care. It's still complaining about the inference stuff, but you'll notice it's not complaining about the Tensor runtime. Sorry, it's not complaining about the NVIDIA runtime, only about the Tensor RT stuff. There we go. If we look here, it says it's running with XLA on a GPU with compute, which is this Here we go. Tesla V100 PCIe 32 gigabyte, compute capability 7. That's excellent. So it's training now on that GPU. There we go. We get our ankle boot. Our inference is done. Jobs are good. Right. We might want to convince ourselves that that's really running on the GPU. So here is a problem. I'm logged in using a screen. I can't put a screen session inside a screen session. It gets really messy. There's another program like that called tmux. Let's do that. Okay. If we run that same script again, I think once it starts training, we should be able to run NVIDIA SMI and prove to ourselves it's running on the GPU. There we go. See? Got the process that's running. It's definitely running on the GPU. Brilliant. Okay. So, job scripts. This is the normal job script you would write. You must be pretty bored of seeing this by now. So we need a GPU one. $lm. This is actually almost exactly what I requested in the QRSH that I'm using for the interactive session. Okay, so remember the steps. We need to bring Python in. 3.9.10. We need to activate the virtual environment. We need to source that environment.show we created. And then we need to run Python. And that should be enough. Let me just check that, make sure in my head. Python, virtual environment, this extra environment variables we need to set. Okay. And we should be able to submit that. Right, our job is now running, which is good. Has it created a path yet? It has, okay. So one of the nice things is all those annoying things that CUDA pushes out that are warnings end up in the standard errors. So we can quickly check that and we can see that it has indeed. The first warning is about not being able to load that in libnvinfer library, which is part of TensorRT, which we decided we're not going to use, or rather I decided we're not going to use because I have only a limited amount of sanity to spend on this. But we also see that it's created a device. It's again running on a V100 PCI Express. That's good. Now let's see if the job actually finishes and if we get our output. So the job is finished. Let's look at the output file. I seem to recall less does not like the term show stuff, so let's see what happens. Ooh. Right, this is fine. Insert a picture of dog on fire here. Recording those progress bars doing the epoch training really produces horrendous output in that file. Okay. We see it ran, we see it trained over the epochs, we see it produced our tensor boot ankle boot image, and it correctly detected it as an ankle boot. So that's excellent. So there we go. We have successfully run it as a job on a GPU. This version of TensorFlow presently works. Future version of TensorFlow may or may not work. As ever, good luck using our HPC systems. And this might be the last video for the year because it's almost Christmas. So if I don't see you again, have a happy Christmas.